Cool. Hello. My name is Sacha, and today I'll be presenting private approximate nearest neighbor search with Sublinear communication. This is joint work with Simon Langowski and my advisor, Srinivas. So nearest neighbor search is the problem of finding points in high-dimensional space that are not too far away from a query. So in this example, this will be the nearest point to the query. Approximate nearest neighbor search is a standard relaxation used in practice that allows finding a point that is close to the nearest neighbor, but not necessarily the actual nearest neighbor. Where is approximate nearest neighbor search used? Well, it's used a lot in recommendation systems. So for example, you might imagine a user that uses Spotify, and Spotify will learn information about the type of music that this user likes to listen to. And this will be encoded as some high-dimensional feature vector in this space. And Spotify might have a database of all different kinds of songs, and they can run approximate nearest neighbor search on this database to find recommendations to return to the user about other songs that they might enjoy listening to. Now, it's not difficult to see that in this setting, the actual feature profile of the user, such as all the music they like to listen to, as well as the song recommendations themselves, are potentially private to the user, and the user might not want to reveal them to Spotify. On the flip side, the actual database that Spotify has of all the different songs and their features might be proprietary information that Spotify wouldn't want leaked to a competitor, and therefore they would like to keep them private from the user. Prior work on approximate nearest neighbor search solves this problem in two ways. One is using two-party computation, and the other is using fully homomorphic encryption. The two-party computation approach is not lightweight for the client or the database and requires about 1 to 5 gigabytes of communication with databases of about 1 million items. Moreover, two-party computation is not maliciously secure by default. So a malicious database can deviate from the protocol and learn information about the client's query, but a malicious client can deviate from protocol and also learn information about the database that it shouldn't have learned. Fully homomorphic encryption, on the other hand, is lightweight for the client because the client essentially only has to encrypt the query and send it to the database. And it's also trivially secure against malicious parties because there's no protocol for them to deviate from. However, fully homomorphic encryption is not lightweight for the database and requires several hours of computation, even for very small databases of about 2,000 items. So in our work, we try and design a protocol that has low communication for the client, concrete efficiency for the database in responding to queries, privacy for both the client and the database, as well as malicious security. The setting in which we operate in is a setting with 2 non-colluding database servers. And you might ask, why do we need 2 non-colluding servers? Well, the short answer is we just need it for efficiency because we want to use symmetric key cryptographic primitives, and this allows us to do so. However, in the full version of our paper, we describe how our protocol generalizes to a setting with a single server and doesn't require this non-collusion assumption. So with these 2 database servers, the client will essentially send a private query to each of these servers. The servers will run some computation and respond to the client. And with this response, the client can recover the approximate nearest neighbor to its query. And in our setting, we'll operate with multiple different clients, so we're not limited to a single client setting. The threat model under which we work is that the 2 servers will hold replicas of the database, and we'll assume that the servers do not collude with the client or each other. The clients, on the other hand, will try and learn as much as possible about the database and may collude with each other in order to achieve this. The guarantees that we obtain from our protocol are accuracy if both servers follow the protocol, user privacy even if one of the servers is malicious and deviates from protocol, and database privacy even if a subset of clients are malicious and collude with each other to obtain information about the database. So now I'll describe how nearest neighbor search is performed in practice using locality-sensitive hashing, and this will form a basis for our Strongman protocol, which I'll describe later. So first, some terminology. So if we have a data set of points and a query in this set, we'll call all the points that are not too far away from the query near neighbors. And all the points outside of this radius we'll call non-neighbors. And within the set of near neighbors, we'll have the nearest neighbor, which will be the closest point to the query. A locality-sensitive hash function, H, or LSH for short, will have the property that the hash of the query will collide with the hash of the nearest neighbor with high probability, but the hash of the query will collide with a point that's outside of a non-neighbor with low probability. So if we plot the distance from the query on the x-axis and the collision probability on the y-axis, the locality-sensitive hash function will have the property that as the distance from the query and a point increases, the probability of collision decreases. And this is very different from cryptographic hash functions that do not want collisions. So using LSH function H, what we can do is we can hash all the points in the data set into a hash table. So we just go through all the points and just hash them into the table. And when a query comes in, we can then hash the query and look it up in this hash table to start constructing a candidate set. So here, the point collided with the first hash key in the table, and so we'll just add that, the ID of the point and the coordinates of the point, or the features, into our candidate set. And we'll just repeat this process with many different hash tables to increase the size of our candidate set. And then, once we have a sufficiently large candidate set, we can then brute force search within the set and find the nearest neighbor by just examining the coordinates or the features. So with that established, I can now describe a Strongman protocol that will use LSH to find the nearest neighbor. So the basic idea is that our two servers will sample a bunch of hash functions and construct the hash tables pretty much as I described before by just hashing the data set into these hash tables. They will then provide these hash functions to the client, and the client can locally hash its query to obtain the hash keys that it has to look up in each of the hash tables. However, at this point, we run into a problem because the actual hash keys that the client wants to look up in each of the hash tables is going to be private information because they're related to the client's query. So the first challenge we have to solve is privately querying these hash tables. Now, fortunately, we can use private information retrieval to perform this task. And in our paper, we actually use distributed point functions, which allow for very efficient querying of hash tables in two server settings. So how does this look at a very high level? Well, the client will send a PIR query to each of the database servers. The database servers will then use these queries to derive a secret share of the bucket value that the client wants to retrieve. But they will do so without learning the actual key that the client is querying for. And the property of these secret shares is that they can be added together to recover the actual value, and so the client can easily obtain all the bucket values when given these shares. So coming back to our Strongman protocol, the client can hash the query locally and then send these PIR queries to the two servers. And if we just focus on one hash table for now, the servers will just process these PIR queries and obtain secret shares of the value that the client wants in each of the hash tables. So after they give these the secret shares back to the client can locally recover the candidate set and then eliminate all the points that are false positives, find the near neighbors, and specifically find the nearest neighbor in this candidate set. So the challenge now is that of database privacy, because the candidate set, as I described just now, will leak a lot of information about the database to the client. Specifically, in this Strongman protocol, the client will learn all the near neighbors and their features, as well as the feature vectors of other points that just happen to collide with the client's query. So if we visualize the baseline leakage, which is just revealing the nearest neighbor ID to the client, the current candidate set is going to leak a lot more. It's going to leak the IDs of the near neighbors and non-neighbors, as well as the ID and the features of the nearest neighbor. So our first step is to provide database privacy, is to change a little bit how we're going to return the candidate set to the client, and we're going to use ideas from Radix sorting in order to prune the candidate set on the fly. So what does this mean? Well, we're going to essentially let the hash function do the work of sorting all the candidates by the relative distance from the query. So what does this look like? Well, if you recall, we have many hash tables. So for the first hash table, we can set the collision radius to be very conservative, such that the probability that a point collides with the query is very low if it's too far from the query itself. However, as we proceed through the tables, we can increase the radius of collision until eventually one of the tables will pick up a point that will likely be the nearest neighbor. And then as we proceed, we'll eventually have a radius that's large enough to capture all the near neighbors. So the key advantage here is that all the candidates in the candidate set will be sorted by the relative distance from the query. And the first non-zero element in this candidate set is likely to be the nearest neighbor. The advantage here is that we no longer need to include the feature vectors. We just need to include the IDs. So this eliminates some of the leakage because now the client doesn't have to learn the exact features of each point. It just learns the IDs of the points that collided with the query. However, this is not enough because the client will learn all the IDs of all the other points that surround the query and maybe even some false positives in the database. So our next tool to hide these IDs that aren't the nearest neighbor is going to be oblivious masking. I'll describe what oblivious masking does. But first, after the servers process the PIR queries, what they'll get is a secret shared candidate set. So I'll denote secret shares with brackets here. And if we recall the baseline leakage, so now that we've eliminated all the features, and so the candidate set now just leaks the IDs. And so what we want, what oblivious masking will achieve essentially is it's going to mask out all the IDs that aren't the nearest neighbor. And so the leakage of this mask candidate set is going to be pretty close to the actual baseline leakage that we want to achieve. The observation that we will exploit for oblivious masking is that all the candidates preceding the nearest neighbor are going to be 0 because there were no collisions at those radii. And so oblivious masking is going to be a very simple algorithm, which I'll describe now. The idea is that the servers will agree on common randomness R1 through Rn, and this can be done easily by just having the servers agree on a common PRG seed. And they're going to copy over elements from the candidate set into this mask candidate set. Now, this is all done locally over the secret shares. They don't have to communicate in order to do this. The rule that each server will follow is that for each copied share, they're going to sum all the preceding elements in the candidate set and add a randomized, the randomized sum to the new element in the mask candidate set. So what does this look like? Well, for the first element, we're just going to copy it over, and because there are no preceding elements, we're not going to do anything to it. For the second element, they're going to copy over the share, but then they're going to sum the previous element, which is just 0, and multiply it by R2, which is still going to be 0, and so that remains intact. And they're going to proceed until they reach the first non-zero element, which is the nearest neighbor ID. But because all the preceding elements are 0, multiplying by R still keeps it keeps the element intact, and so the nearest neighbor ID is going to stay intact. However, here comes the interesting part. For all the elements following the first non-zero element, the sum is going to be non-zero. And so when we multiply it by the randomness, the resulting value is going to be uniformly random. And so essentially, for all the following elements in the mask candidate set, they're all going to be uniformly random and completely hide the original values that were contained in the candidate set. So at this point, what the client will obtain is a candidate set that looks something like this, where all the elements following the first non-zero element is going to be uniformly random. And what this results in is that the client learns nothing beyond the ID of the first non-zero value. So we've essentially masked out everything following the nearest neighbor ID. However, the client does learn how many zeros precede the nearest neighbor ID, and so this results in a little bit of leakage, which intuitively corresponds to the approximate distance between the query and the approximate nearest neighbor. In the paper, we showed that this is actually optimal asymptotically, but in practice on real-world data, it could be up to 15x more than the baseline leakage in the worst case. So now I'll turn over to evaluation. We evaluate our protocol on 4 real-world data sets: Deep1B, SIFT, GIST, and MNIST. These are all standard data sets used in nearest neighbor search benchmarks. So on the small data sets, so approximately, so MNIST, which has 60,000 items, to achieve accuracy of over 95%, we require about 300 milliseconds of server-side computation, and the communication remained under 1 megabyte between the client and both servers. Here, the number of probes is just the number of buckets we retrieve per hash table. On the larger data sets, so 1 million items and 10 million items, we require 1.2 seconds of server processing time per query and 8 seconds of processing time on the 10 million item data set. And the communication remained between 1 and 2 megabytes. So this is 5 orders of magnitude less computation compared to FHE-based approaches for approximate nearest neighbor search. And it's about 1 to 3,000x less communication compared to the two-party computation-based approaches. Thank you. Happy to take questions.
Thanks, Sacha. If you have a question, please use the microphone.
Hi, Mingxun from CMU. This is a very great talk, thank you. And I wonder, how could you quantify the leakage? Because you said compared to the baseline leakage, you have 2 times to 15 times in practice. Mm-hmm. I wonder, what does that mean?
Yes, so the way we do this in the paper, it's quite involved, but the idea is that depending on the data set, we have to have different radix buckets in order to be sure to find the nearest neighbor. And so we look at what the largest radix difference, like the granularity of the radix buckets, and we look at how much more that is relative to the baseline, which is leaking nothing. Oh. So essentially, the radius at which the nearest neighbor collides is going to reveal some information, some distance information, intuitively. Yeah.
Okay. Thank you.
Can you speak a little bit about how you make the radix approach and the masking work in the single server case?
Yeah, so the oblivious masking stays pretty much the same, except it operates over homomorphic encryption. The radix sorting stays pretty much the same. The only thing that we need, the only reason we need the 2 server setting is actually to query the hash tables using a distributed point function. And so that's what makes everything a lot faster. All the other primitives remain pretty much the same.
You said it's maliciously secure,
yeah.
But it doesn't defend, at least what you described, doesn't seem to defend like from a malicious server sending something wrong, then the first
yes.
few entries wouldn't be 0, and then the client would get garbage, maybe.
Yes, so we specifically mean that malicious security against privacy. So that means like if either party deviates from the protocol, then privacy remains intact, even though correctness is not.
Okay, but you don't have anything like that the client could check if what the server sent is.
So you could actually easily do that in the 2-server setting, because if one of the secret shares is corrupt, it could tell that one of the secret shares was corrupted. But that would require additional analysis. Yeah.
Okay, thanks.
But in a single server setting, that wouldn't be possible.